Okay, welcome back again. So, as promised, so today I'm doing something extra which is out of your normal classes. So, it is going to be, I mean, linear first order PDEs, and of course, along with this, the method of characteristics. Okay. So in fact, later on you will see that the method of characteristics we have already introduced. I have already introduced you to that, but it was kind of latent. It was hidden. Okay. So let us consider a first order linear PDE in this form. Say suppose it is given in the general form AXY your JX plus BXY JY plus CXY J, and this is equal to something like D of XY. Okay, so of course, A, B, C, D, they are functions. They have been defined in some, say, region. Omega in R2. You already know it, and of course, we are seeking a solution J equal to J of xy of this equation. Call this equation as 1. Is it okay? Fine? Yes. Okay, fine. So, and again, like say, I am assuming that this A, B, C, D, they are C1. They are C1 in omega. Okay? So, now, again, this equation, I can write it as, like, your this factor will be, so this is equal to minus C xy j plus d of xy. Right? Is it okay? Fine? Yes, sir. Just simply I have written in terms of dot product here. Okay. So basically what it is, if you look at this, if you consider the function of two variables, say, f of xy, so then you recall that the directional derivative of this function, right, along a vector given by, say, AB, along a vector AB, it was simply given by grade of f dot AB. Isn't it? Fine? So that means what is happening out here? Like this is actually in the form what? This is actually in the form grade z, right? Dot AB. Isn't it? The term on the left hand side here. Okay. So that means this represents the directional derivative of the function j as a function of two variables x and y in the direction of a comma b. Fine? Okay? Yes. So, when the vectors are a and b, they are constants. So it is going to give the vector, like say, if a, b, say, suppose they are constants. Basically, I am considering, say, this. Say suppose this is constant, a, b are constant. So it is going to give you a fixed direction, isn't it? Now, if it is not constant, in fact, I have already introduced you to that. That concept's true. The concept of integral curves earlier, but let us try to understand it a bit differently. So now, what is going to happen? And remember, the original differential equation I'm simply referring to as 1. Okay. So now, what is happening out here? Like, let it be here. See, now, what is going to happen? Like, suppose, B is given by this axy bxy, right? So then suppose I'm considering, say suppose this is xy, this is r2, and suppose this is my omega, say this is my omega. So then what is going to happen? Like at each point here, I can get a vector field defined by this vector v, isn't it? Fine. Okay. So now what is going to happen? Say suppose I introduce a system of equations given by, say, dx dt, dx dt. Say suppose I introduce it as a function of, say, xt yt, and dy dt, and dy dt, again, say suppose this is xtyt, and then what is going to happen? These two equations, say suppose I call it 2, these two equations, they are nothing but what they are going to represent. They are going to represent, say, suppose I define a curve in your xy plane, in xy plane through this vector. So basically I have a vector like this. I have a vector like this. Say suppose this is the vector RT, and suppose this curve, a particular point is P, is designated by xt comma yt. So definitely through this vector I'll be able to define a curve like C, isn't it? Right? And this curve C, so that means I have parameterized this curve through the variable t belong to some interval I, right? And this is going to define this curve. Okay? So that means what is going to happen? Like, and again you know that a tangent to the curve, it is simply given by this vector dx dt, dy dt. Right? So that means these two equations, they are going to define a curve in xy plane, right? On which I mean the vector given by this is tangent at every point. Clear? Fine? Yes, sir. Okay. So what we are going to do, let this curve, maybe let me call this curve as C1, not as C. Because I would like to use the initial curve, I would like to use the symbol C explicitly for the initial curve. Okay, fine. So this is a curve in xy plane where at each point of the curve, I mean this V is a tangent. That's it. Okay, fine. So now what is going to happen along that curve C1? If I want to find out, as before, I mean, I think now you have done it umpteen number of times. So you know that this is simply Jx dx dt plus Jy dy dt, isn't it? So then if you recall, my original equation was something like a xy zx plus b xy zy plus c xy j equal to d of xy. Is it okay? Fine, isn't it? So basically, I mean, this is what z of x for this function, as a function of two variables x t y t, and again, so this is simply, I mean, ddt of, I mean, x as a function of so I can simply no, sorry. Because here what is going to happen? See, this one, this derivative, I am considering along this curve. So then I have already have this equation 2 representing the relation between dx dt, right? And here you can see that dx dt is simply a of x t y t, right? So similarly, this is zy as a function of this into b x t y t, right? Is it okay? Fine. But from the given equation here, which I call it 1, you can see that this is nothing but minus cxyj, right, plus dxy, isn't it? And then what we are doing here, what we are doing here, eventually what is going to happen, like this eventually, so this is equal to minus c, I'm just putting some, okay, of course it is c xy d xy, right? But because I have considered it along the curve c1, so obviously, right? So now what is happening here? So that is why I can simply write this as a function of just a minute. This j, I have this j. This into j. J, of course, just a minute. Let me write it down a bit. So this is simply minus c as a function of xy into j plus this. Okay, fine. So that means this is simply what? Eventually, this is a function of t, right? Again, j is a function of t, I can write explicitly, and this is simply t now becomes a function of t. Yes. Right? So that means what is happening out here? What is happening out here? Along the curve c1, what I am getting, eventually I am getting, of course, this was dz. Eventually I am getting this plus ct jt equal to dt. Is it okay? Fine. So what does that tell you? What is happening out here? Along the curve C, right? From the given equation, I have got another differential equation, or what I can tell you is that along this curve, the given equation, it has reduced to an ODE. Isn't it? Fine? Okay. So now you can easily solve this ODE. Isn't it? Right? You already came across this. Huh? So this is what you do. You simply find out the integrating factor, and integrating factor is given by mu t. Integrating factor is given by mu t, and this is equal to what? This is equal to exponential 0 to t, then something like c tau theta. Isn't it? Right? And then I can easily solve this. Differential equation. So this differential equation as what? Simply t is going to be 1 by mu t, and then your 0 to t, your mu tau d tau.
It's C tau.
Sorry. C tau d tau, right? No. Is it going to be C tau d tau? Just a minute. No, it is D. It is D. It is D. D. It is
From
D.
the starting.
No, it is D term.
Okay.
It is D term, not C. It is D term. Okay, fine. And then plus the initial value of it is going to be something like this. Okay, fine. So now, what does it tell you? Like that there are three things that is coming out of this equation. Coming out of this equation. So let me call it 3. Let me call it 3. So what is that? Now obviously your mu t, it depends upon ct, right? Mu t depends upon ct. So again, while you are computing zt, you need mu t, which depends upon ct, right? You need dt, right? So basically, if you want to solve this given equation, simply what you simply need these two expressions. You simply need these two expressions, isn't it? In order to solve it.
Yes, sir.
Is it okay? So now let me come back to these equations. Let me come back to these equations. So I have got that one. Okay. So let me just come back to this. Say dx dt equal to axy, dy dt equal to dxy. Okay. So this set of equations, which I think I called it 2. So they are called the characteristics equation. They are called the characteristic equation. Okay, and again, like the solution of this characteristic equation, it is called the, and of course they are going to give you some curve, isn't it? They're going to give you some curve, so it is called characteristic curve. So let me tell you what is happening. Characteristic curve. See, remember, I'll tell you what is happening. Let me try to give you a pictorial representation of that. In fact, you have already got introduced it in my previous classes when I was considering quasi-linear differential equation. So, see what is happening out here. Here, I have some say curve, initial curve. I mean C1. Sorry, not initial curve. Sorry. I had a curve C1. So C1, it was such that at each point of C1, this V given by your AXY, comma BXY, right? It was a tangent. Is it okay? Fine. So then we parameterize this curve C through. So this is nothing but tangent say T bar, and this is given by this. And what we had, we kind of like say, suppose this is R. So we parameterize R simply by this xt yt, right? For some t belonging to I. Okay, so now you can see that along this curve, for all the values of t, you can solve for j. Is it okay? Fine? You can solve for j, right? So now, what is happening here when you are solving for j? So that means for each value of t here, you are going to get a point in space, right? So what is going to happen? That is going to define another curve here, right? So let me call it say C1 maybe C1 tilde, C1 tilde. Okay, so in some books you will find that they call this curve also as a characteristic curve. Is it okay? But basically, if we concentrate here itself, the curve in xy plane, right? This is, I mean, more specifically, this one is called a characteristic curve in xy plane. Because see, this one is good enough for us. This one is good enough for us because based on the given differential equation, what we can do, I know that along this characteristic curve, the given equation reduces to an ODE, right? And I can solve that ODE, right, for all the values of t belonging here. That is going to give me the values of j, right? And then by roughing in all the points x, y, j, I can get another curve here. Is it okay? Fine. So this is called a characteristic curve. Okay, fine. So now, okay, whether I have finished, I have covered everything or not. Let me see. Okay, characteristic equation, characteristic curve. I have already had. And now, okay, see, another thing here is that. So now you know that these two, I mean, these two equations of this system of equations given by 2, what is happening? They are nothing but some ordinary differential equations. They are nothing but some ordinary differential equations, isn't it? So now what is going to happen here? So if you have certain initial condition, like say suppose I have some initial condition given by x naught y naught. So that means x at some t equal to t naught and y at t equal to t naught is given by x naught and y naught, right? So then if your right hand side are continuous, then you know that continuous, or if it satisfies the Lipschitz condition, right? These two equations. So then you know that a unique solution exists, isn't it? Fine. So that means the curve that you are going to get from this, that is going to provide you with a unique solution. I mean, it is going to be a unique curve. Okay. So every characteristic curve here, it is going to define a unique curve. Is it okay? Fine. So now let us come to the method of characteristics. Okay, let us come to the method of characteristics. Okay, how you are going to solve an initial value problem with the help of the method of characteristics. Okay, fine. So maybe what I will do, let me just erase. So now I will come to the method of characteristics, which I am going to call it a method of characteristics for solving solving an initial value problem. Solving an initial value problem. Okay, initial value problem. So what is going to happen here? Basically, what we are trying to do, we are trying to solve this equation, say axy zx plus bxy zy plus cxyj equal to dxy. Okay, and it is subject to some initial condition. It is subject to some initial condition where, I mean, your j will be given as a function of xy. Okay, for some curve, say for some initial curve, I mean initial curve c lying on xy plane. Okay, I mean whose values will be given and the corresponding values of j also will be given. You already know it, right? Initial value problem. Okay, so here what we are going to do. See, obviously, you know that. Like, say, suppose, say, this is, of course, now, see, this initial curve, although I was telling that this is in XY plan, this is in XY plan, because I'll be already having the values of J, right? So that means, what I will have? I will have an initial curve C in XYZ space. Okay. So now, suppose I parameterize this initial curve through some parameter, say S. So x equal to xs, y equal to ys, and z equal to, say, js. Is it okay? Fine. So that means, I mean, and for some for some s lying in some interval, say I1. Okay. So then, what is going to happen? What is going to happen? And again, remember that the extent of this curve may be finite or infinite. Okay. So then, what is going to happen? For each values of s, for each values of s, say suppose I'm saying that okay, this is the particular values of s. Okay. So then, what I can do? I can draw a characteristic curve through each point lying on this initial curve, isn't it? Are you getting my point? Is it okay? Fine. So then, my situation is going to be something like this. Say, suppose this is my, this is my characteristic curve passing through a specific value of s. Okay, fine. So then, what is going to happen? This characteristic curve, what I have for this, I now with each point, I can have a characteristic curve, isn't it? Right? And from the existence and uniqueness theorem, these characteristic curves, they are going to be unique. Is it okay? Fine. And then what we are going to do, as you already know, out of all of them, what the union of all those characteristic curves, each of them passing through a point on this initial line, I am going to get a surface, right? And that surface is nothing but going to be the integral surface corresponding to this equation. Okay, fine. So that surface is going to be given by some function z equal to xy, and that is going to be the solution of that initial value problem. Is it okay? Fine. So now let us see how we go about it. Okay, fine. So now again, now what we can do? I can parameterize this characteristic curve the way I did earlier, isn't it? I can parameterize this characteristic curve the way I did earlier. So what is the way to do it? See, suppose I am considering this particular characteristic curve. Suppose I am considering this characteristic curve passing through this. So what I can do? I could have like say parameterize it. I could have parameterize it with something like xt, like yt, right? And jt, isn't it? Fine. So now what is happening? For each s, I am going to have such a characteristic curve, isn't it? Is it okay? Fine. So that means eventually I can have a parameterization of all x comma y comma j lying on this surface through this representation of xyj as a function of two variables s and t. Is it okay? Fine.
Yes, sir.
Is it okay? isn't it? So then what is going to happen? What is going to happen? Now remember, this is very interesting. See, S was varying along this, right? T was varying along this, isn't it? So what we can do for each value of S, we are going to get one curve, right? So that is why I can think that the initial curve whose parameterization is nothing but xs, then ys, and then zs, I can take them to correspond to when t equal to 0,
Yes, sir.
right? I can simply think them to be something like that. Fine? Okay? So, for parameterization like this, I am going to have my initial curve C given by this. Initial curve C given by this. Is it okay?
Yes, sir.
Fine? So, that means the functions x st, y st. So they are going to satisfy this equation. D dt of st. So this is equal to what? A of your xt yt. Is it xt yt? Because now my business is growing. Right? Okay?
Yeah.
And this is going to be satisfied along the characteristic curve. Remember. Because this A and B, remember, they came from the original differential equation, right? And when we were talking about directional derivative there, is it okay? Fine? Okay? Fine? And here, what is going to happen? These are, see, the situation is something like this. This is my C. Huh? This is suppose this point, because C I have parameterized initially through the parameter S, right? Say suppose I have, this is nothing but a C1. This is a characteristic curve, right? So here what is happening out here? Like this is C, the initial curve. This is C1, characteristic curve. So now you remember that if I have to solve for J, along this characteristic curve, basically there is going to be what? Its projection on xy plane is going to be there, right? Isn't it? For that I have got some parameterization definitely given by xs and ys, right? So in order to solve for J, for these two equations, I will be needing an initial condition, isn't it? Right? And that initial condition, it is straightforward. It is simply going to be given by this. Are you getting the point?
Yes, sir.
Right? Say these are going to be coming from this curve. Remember the initial curve. Is it okay? Fine. So now my job is done. My job is done. So now what is happening? See, along each of those characteristic curves, so now my J as a function of xy, it has reduced to simply this x as a function of st, y as a function of st, right? So eventually, again, z has also reduced to a function of s and t along each characteristic curve. Remember, which is eventually going to embed the whole sorry, whole solution surface. Is it fine? So similarly, your C is also eventually it is going to become a function of ST eventually, and then D also it is eventually going to be a function of ST, right? Okay, so that means that, and I already know how to solve the equation for finding J along each of these characteristic curve, because you remember that your JT, if you recall it correctly, it was given by this it was given by what, 0 to t your mu tau d tau d of tau, this plus j of 0, right? J of 0. So now, if I assume that for this function j, the initial condition was given by j of s0, this is equal to g of s. So then, what I can do, I can solve for j as a function of s and t from this. Now I can consider mu as a function of, say, s and t, and then this will be simply 0 to t, mu as a function of s and t, d as a function of s and t, dt, and instead of j0, this is simply going to be g of s. Is it okay? Fine. I think just I have to, yeah. Fine. Okay. Okay. So now, see, like say I have to do one particular exercise, then it will be clear how through this method of characteristic you can solve a given differential equation. Okay. So I think I have to be pretty quick. I have got another 15 minutes. Now remember one thing. See, my original equation was in variables x and y, isn't it? But I have found out them in terms of s and t, right? So definitely you would like to, convert s and t back to x and y, isn't it? Right? So now, for that, what must happen? If I have to retain your x and y from s and t, right? See, I was considering s as a function of s and t and y as a function of s and t. So if I have to retain x and y back from s and t, what condition must be satisfied? The Jacobian of xy with respect to, st, j given by this, it must be non-vanishing, right? So that means xs yt minus ys xt, it must be non-vanishing. Is it okay? So this condition has to be there. So let us try to work out one example, and I'm taking it from your Tau book, ux plus uy. Equal to x and u x0 equal to x squared. Okay, fine. Okay, so here you can see that your axy is y, bxy is 1, right? Cxy 0,
0.
isn't it? And dxy, this is equal to x. Okay, fine. And what is being given here? Now the parameterization, of that curve. So this is my initial curve. This is my initial curve, isn't it? So my initial curve C, it will be given by this parameterization. See S 0 S squared, right? Isn't it? So that means your x S0 equal to S, y S0, this is equal to 0, right? And Z S0, again we had defined it as ZS, this is equal to S squared. Is it okay? Fine?
Yes.
So then, again I have what? Dx dt. Now I have to write it as a function of A, your st, isn't it? AST. So now see, it was
Y.
y. So it will be simply yst. Is it okay? Fine. This is the first part. And then dy dt, this is equal to
1.
dst. This is 1. Okay? See, here I still don't know. These are simultaneous differential equations. Right? So how we are going to, so now this is what? So this means y equal to t plus some constant, because here s is kept fixed. I am going to call it, say, C2s. Okay, so y is a function of s and t. Is it okay? So basically y is a function of s and t. This is this, right? So if I use initial condition, so now y s0 equal to 0 plus C2s, and y s0, it was what? 0, isn't it? This is equal to 0. So C2s is going to be equal to 0, right? So that means yst, this is simply t. Is it okay? Fine?
Yes.
So then if I plug in it here, the value of yst, so this is simply t. Fine? So that means your xst, so this is t squared by 2 plus some constant, right? Which is a function of s. And again, this implies x s0. So this was what? X s0 was equal to s. This is your 0 plus c1s. So basically your c1s
Is S.
s. Okay? So that means what I have got? I have got xst, this is equal to t squared by 2 plus s, and yst, this is equal to what? Your t. Fine? Okay? Fine. So let me, okay. I think I can now erase this, right? Because I want to keep this. I have to find J now. Okay. C is here, right? Okay, anyway, C you remember. I can don't worry. I simply need the original equation. That is good enough for me. Okay, fine. So now, in order to find out J, I need that integrating factor, isn't it? So what was mu t? What was mu t? Mu t was exponential 0 to t c tau, this something like this, isn't it? And c was 0 here, isn't it? So it will equal 0, this is equal to 1. Is it okay? Fine? Clear? Okay. So now you recall J st. This was 1 by mu st, right? Then 0 to t, and then mu of st, d of st, dt plus g of s, if you recall. Fine? And this is already 1 mu of st, and then this is 0 to t, this is 1, and d of st was what? D of st, x is simply what? This,
Yes, sir.
isn't it? D of st will be that one. So that is, so from here I can write d of st, this is equal to x, this is equal to t square by 2 plus s. Okay, so 1 into t square by 2 plus s dt, and g of s, that was s squared, if you recall, right? Because it came from here,
Yes, sir.
if you recall. So this is s. So so then like from here, what you are going to get, so it is going to be 1 by half t cubed by 3 plus st plus s squared. Okay, fine. So now if I plug in the values, if I plug in the values of s and t in terms of x and y, so this is your y cubed by 6 plus s is x minus y squared by 2, and then t is simply y, and then again x minus y squared by 2 whole square. Fine. And then you will see this is minus y cubed by 2 plus y cubed by 6. So that makes it minus 2y cubed by 6, right? So it is eventually that is going to be y cubed by 3, and then your xy, and then in fact this problem I have taken from that Thaw book, and they are treating it differently, but eventually I mean they have also reached the same solution. Okay, so yeah, I think we are fine. Okay, so now let me try to do an exercise which is kind of, it's going to be easier than this, but that is a very famous problem, or it's a very famous equation, although it's a very simple one. You will see what I mean by that once I give you the exercise here. Okay. So, fine. Okay. So you must have seen that umpteen number of times. Say ut plus cux. This is equal to 0, and your initial condition is given by ux0 equal to some function of x. Okay? Can you recognize this equation? This is nothing but 1D convection equation, right? Okay. So now let me write it in x, y, and j form so that it is easier for us to parameterize in terms of s and t. Okay. So here your t is time. Okay. So and again remember, although the variable u is being used here, so you can use, I mean, instead of dz you can use du also. So I'm simply converting u into j. Don't worry about it. So if I want to write it in x, y, and j, Again, it will be something like what? You see Jx plus Zy equal to 0, and your initial condition is given by Jx0 equal to f of x. Okay, fine. So here the initial curve can be parameterized by this one. You're simply s0 f of s. Is it okay? Fine. So that means your x s0, this is s, y s0 equal to 0, and j s0, I mean this is, I write it as 0 of s, and it is nothing but given by f of s. Fine. So, and again your axy that is a constant, your c, your bxy, this is equal to 1, and both cxy and dxy, that is equal to 0, right? So that means your mu of t, this is e to the power minus, simply it will be 0 d tau, so it is simply 1. Okay, fine. So now if I use the characteristic equations, yeah, so then what is going to happen? So dx dt, so this is equal to axy, and again now x and y I have to convert it into a function of s and t, but here it is straightforward because this is simply a constant, right? So similarly your dy dt, this is 1. Okay, so from here you can see that I can write simply your x of st, so this is equal to ct plus say c1s. So then, I mean initially when t was 0, your x was given by s, right? So that means your like say s0, this is equal to s, and this is equal to 0 plus c1s. So that means c1s is simply s. So that is why your xst, this is simply your ct plus s. Okay, and from here you are going to get what? You are going to get y equal to t plus c2s, and of course this y as a function of s and t. So from here y s0, this is equal to 0, so this is 0 plus c2s. So c2s is simply 0, so therefore your y, it is simply t. Y is simply t. Okay, fine. So that means what we got, I have got xst, this is equal to ct plus s, and yst, this is equal to simply t. Okay, fine. So this is done, and then you know that j is kind of what 1 by mu st, then 0 to t. What was there? Mu st dst dt plus g of s. Okay. So now your d is 0. D is 0 here. We have already figured it out. So this part is going to give you 0, and mu is already 1. So eventually I am going to be left with only g of s, and g of s was simply f of s, right? So this is going to give you simply f of s. Is it okay? Fine. So now what we have to do, we have to convert your s and t into x and y. So here you can see that your s from here you can see that just a second. See from here your y equal to s equal to your y, and from the first equation your not s equal to y, t equal to t equal to y, and from the first equation what I get, x equal to ct, t is y plus s, so this implies your s equal to x minus cy. Okay, so eventually what I can do, if I want to write z as a function of x and s, so that is going to be giving, again I'm going to say x and y, so this is f of s, and s is nothing but x minus cy, okay. Then one interesting observation I connected with this particular problem. Okay, let me tell you what it is. See, if you look at this, so now I mean, if you recall the original equation, it was given in terms of something like what, ut plus cux, this is equal to 0, and then your u at x0, that was equal to f of x, right? So now if you write down the solution, u as a function of xt, so this will be simply x minus ct, isn't it? X minus ct. I mean now, t represents your time. Okay. So now, what does it tell you? See, you have one initial profile here. Say, suppose this is my okay. Say, suppose this is my x line. This is my t line. Okay. So basically, what is going to happen? So this is 0. So this point corresponds to t equal to 0. This may be something, I mean, non-zero t, and t is progressing along this line. So now, this f of x, this is nothing but some initial profile. Okay. Say, suppose your initial profile was something like this. Say, suppose initially your profile is say something like this, something like a triangle. Say. What I mean to say is that, and if so, this is the initial profile given by f of x. What does f of x minus ct means? So this means that at time t, the initial profile is simply shifting ct units towards right, isn't it? So then what is going to happen? Say, suppose if you take say t equal to 1, say suppose this is 2. So at time t equal to 1, this initial profile is simply going to shift what? C units towards right. So now suppose that I mean, say suppose this distance is say c. So that means this wave is going to move c units towards right. So if say if I draw something like that, if say suppose this point corresponds to this, so that means what is going to happen? Right now it is going to shift here, right? So at time t equal to 1, it is going to be like this, okay? And then at time t equal to 2, it is going to be something like this. So now you will see that if I join all those points, where I mean I have taken this discontinuity in the solution here. So then you are going to get a straight line. You are going to get a straight line over xt plane, right? And you will see that this discontinuity is propagating along that line. Okay. And if you consider, I mean that line, you will see that the equation of that line is nothing but something like x minus ct equal to x naught, where I mean this is x naught, because it is simply x, it would have been x minus c t naught, but here t naught we have taken as 0, so that is why it is simply x naught. So what is going to happen? Like the discontinuities are propagating along these characteristics. Discontinuities are propagating along the characteristics, because if you look for this characteristic equation, so what I can do, I can simply solve it through what? dx by c equal to dt by 1, isn't it? Right? So from here you are simply going to get it as x minus ct equal to constant, isn't it? So these are nothing but this characteristic line. Is it okay? So this is a very famous example. This is nothing but 1D convection equation. Is it okay? So with that note, I'm going to finish today's class. So probably in our next class, we are going to discuss more into this characteristic equation. So maybe I will try to get into Cauchy-Kovalevsky's theorem. Okay? Okay, then I'll see you in my next class.